All right, so explicit versus implicit. I kind of already mentioned this a little bit, but explicit functions are things that are solved for y or f of x already, okay? Then we can just take the chain rule or do whatever derivative we need to, product rule, quotient rule, all that kind of stuff, take the derivative. Things on the right-hand side have x squareds, y cubes, and y's. There's no way that I can solve for just y and take the derivative, okay? So we're going to be looking at problems that look like this today, implicitly written, and we're going to take the derivatives of those things, okay? So example 1 here is kind of going to get us set up, starting to solve with respect to x. It says solve for x. I actually want to cross that out, and we're actually going to solve for y. Okay, so if I solve this equation for y, divide by x on both sides, and I'm left with y equals 1 over x. Okay, which that's the same thing as x to the negative 1 power, right? Which we know how to take the derivative of that. What is the derivative of x to the negative 1 power? Negative 1x to the negative 2nd power, right? Power rule says move it down in front, subtract 1 from the exponent. So this is the same thing as negative 1 over x squared, okay? Now also the notation-wise, it can be y prime, or remember we can also use the notation of the derivative of y with respect to x, right? That means the same thing as y prime. Okay. Now, this second example here, or this, kind of part B of our first example, it says that we want to differentiate with respect to x using the product rule, okay? So if I take and do the product rule on the left-hand side here, we're going to have to use that idea of d, not x on top, but dy on top with respect to x, okay? So what does that look like? That means I'm taking first, and I'm just going to write x down. And then I'm going to take the derivative of the second piece, okay? Because I've got two chunks here. I've got the x and I've got the y. There's two things being multiplied together. There's two functions, right? So what is the derivative of y with respect to x? How would I write that? It's a fraction.
Y over dx.
dy over dx. Yeah, the derivative of y with respect to x. Okay. Then I take and I do the derivative of the first function. Well, what's the derivative of x? 1 times the second function of y. Okay, some of us might have this flip-flopped, and that's okay. If I'm taking the product rule and you switch that order, that doesn't matter. As long as you're taking the derivative and then timesing it by the original function of the other and vice versa. Then what is the derivative of 1 on the right-hand side? 0, okay? Okay, so now I want to solve, question. Okay, so now what we need to do is we need to isolate my dy dx, okay? So I got to do a little bit of algebra. So I need to move this 1 times y over to the right-hand side. So what am I going to do? Subtract it, right? So I've got x times dy over dx equals negative y. Okay, well, how do I get the dy dx by itself? Divided by x, right? So divide by x, divide by x. That goes away, and we're left with that dy dx is equal to negative y divided by x. Okay, so we just found the derivative 2 different ways, using the product rule and doing it how we've done before by solving first for y, okay? However, do these two things look exactly the same? No. The reason for that is because in the second one that I did, okay, using that product rule, I have a y here, okay? Well, didn't I know that y is also equal to 1 over x? So this is actually the same thing. If I plugged in 1 over x for y, and I divide that, don't I also get negative 1 over x squared? Yes? Do we see that? Okay, so these things might look slightly differently, but they are the exact same derivative. We took the same derivative, okay? It just looks a little different. We can plug this in right now because I can solve for y, okay? In the future, in problems, we are not going to be able to solve for y, which is why we have to do it this way, okay? By taking and doing, what am I trying to say? The implicit differentiation, okay? With the dy's and the dx's, okay? All right, let's move on down here. So these next three examples are all going to be the exact same problems, but just to get us practice in what we are differentiating with respect to, we're going to change up the variable, okay? So for this one, it says differentiate with respect to t. Since we must apply the chain rule, each derivative is going to have a dx or dy as part of the derivative, okay? Because I've got x's and y's here in my function, okay? So I'm going to take the derivative of y cubed. If I take the derivative of y cubed, I get 3y squared. But then what is the derivative of just this piece of y in relation to t? That would be dy over dt. Okay? This variable can change, whatever it's in respect to. So whatever it's in respect to, that goes in the denominator. Okay? All right, then let's take the derivative of y squared. The derivative of y squared would be 2y. With respect to t, I need to multiply this by dy dt. Okay, moving on, I've got minus x squared. So that would be minus 2x times d what on top? Dx over dt. And that equals the derivative of negative 4, which is 0. Okay? I'm not doing anything else right now. This is all we're doing for these next few problems, so that way we get practice with how do we rewrite it in terms of these different variables that we're differentiating between. Okay? All right, moving on to the next page. Oops. That was it for that one, yes. Okay? Because this next one, part B, of the exact same type of problem, it's the exact same function. However, we are differentiating it now with respect to w. So the only thing that's changing is the denominator. Instead of it being dt, it is now dw. So on the top, it's going to be either dx or dy over dw when you're evaluating it. Okay? So just write out the derivative of this function. All right, did we all get this up here? Yeah? Okay. And then you got one last one. This time we are differentiating with respect to what variable? With respect to x, okay? So that means, same thing, we're either going to have dx or we're going to have dy as part of our derivative, okay? So let's take the derivative here. It's the exact same thing we've been doing, so it's going to be 3y squared dy dx plus 2y to the first dy dx minus 2x d what on top? dx. Okay? And then on the other side, derivative of negative 4 is 0. Okay, we already kind of talked about this. dx over dx, that's just going to give me 1, right? So if you're taking the derivative of a function with respect to that variable, you don't need the dx over dx or the dy over dy, that kind of stuff, okay? You only need it when it's not the variable that you're taking the differentiating of, or sorry, taking the derivative of with respect to is what I'm saying, okay? So now underneath it, it says to use algebra skills to rearrange to solve for dy dx. Okay, so if I am trying to solve for dy dx, that means I am trying to isolate these two things right here. How am I going to do that? Add 2x to both sides. So let's rewrite this as 3y squared 2y. Okay. So now I can take out a dy dx on the left-hand side from both of those functions on the left. So now I'm left with dy dx times 3y squared plus 2y. Are we okay with how I pulled that out? And then that just equals 2x on the other side. And then to isolate that dy dx, I have to get rid of that 3y squared plus 2y. So I would just divide by it on both sides, right? So your final answer would be dy over dx is equal to 2x divided by 3y squared plus 2y. Okay, that is my derivative of our function, which means I could plug in some values if I wanted to figure out what the slope is at 5. I could plug in 5. I could plug in 3 and find out what the slope is going to be at 3. Okay? Questions on finding that derivative? Okay, then let's try out these few problems down below. They're a little simplified in terms of the ones that we were just doing. So letter A is a problem that we've been doing for a while now, and it's using the power rule. If I take the derivative of x cubed, that just simplifies to give me 3x squared, technically times dx over dx, right? Technically. But we know dx over dx is just 1, so this is actually 3x squared. Okay. Now, looking at letter C, if I'm taking the derivative of these two things being added together, that means I'm taking the derivative of x and I'm taking the derivative of y and I'm adding that together, right? So what is the derivative of x with respect to x? 1, right? Technically times dx over dx, but that we don't need to put that. Okay? The derivative of y, now since y and x don't match, right? I need to make sure I am evaluating that derivative with respect to x. So this would be just 1 times dy over dx. If this was like a 4 instead, this would also be a 4. Okay, does that make sense? But it's a 1, so we're not going to add that in there. So I've just got 1 plus dy over dx, the derivative of each of those pieces with respect to x. Does that make sense? Okay. Now, looking at letter B I can still use the power rule for. If I use the power rule, I get 3y squared. However, it is not it is with respect to x, right? So that means I need to multiply this by what? dy over dx. And that is your answer. Okay. Letter D, this is when people start getting a little confused, is because I don't have just one function here. I have two functions, right? X and y squared. Those are two things right there, right? So I'm going to have to use what in order to find the derivative here? The product rule, right? So the derivative of this product rule would be x times the derivative of our second piece. What's the derivative of y squared? 2y times dy dx. Okay, then we add that with, we're going to leave the y squared by itself and take the derivative of our first function, which is just 1. The derivative of x is 1, right? Again, you might have these flip-flopped from your product rule in your brain, however you have it thought of and saved in your brain. The order does not matter as long as you have the same things multiplied together. We're ideal, okay? So that is your answer for that one, okay? Any questions on those 4? All right, moving on. I think that's the last one on this page. Okay, here are all of your rules that we just kind of went through when we were solving these problems for implicit differentiation, okay? You take the derivative of both sides with respect to x or whatever variable it tells you to take the derivative with respect to. And then you want to get all of your dy dx variables on one side. It doesn't matter if it's the left or the right, but get them all on one side and then move everything else to the other. The factoring out can be kind of tricky, the algebra piece there. And then after you factor it out, you can divide both sides by whatever does not have that dy dx term, okay? So example 4 is very similar to the one that we did. So I want you guys to try finding the derivative of this function with respect to x. Check with your neighbor, and then I'll go over the answer here in a few minutes. Okay, try it out without looking back at your example that you just did. Feel free to watch along if you are unsure. Did we all have the dy dx with just the 5? Good. Okay, so if you just left your answer like this, that would not be quite right because it's asking us to find dy dx. So that means I need to isolate, which means I need to pull it out of all of these and get that 2x over to the other side. So I'm going to kind of do both of those steps in one. So I'm going to take out that dy dx, and I'm left with 3y squared plus 2y minus 5, and then I have 2x on the other side. So then dy dx is just 2x divided by all of that stuff. Okay. Questions on any of that? Okay. Now, this next one's actually going to have a little bit more, like, we find the derivative and then we can actually use it to find some stuff like we've been doing, to find the tangent line, to find the slope at a point, that kind of stuff, okay? So, instead of us pulling out Desmos, I will just tell you what this graph here, x squared plus 4y squared equals 4 looks like. Anyone have a guess of what it looks like? Yeah, it's like an ellipse kind of thing, right? So it's going in between, oh, that was a terrible circle there. It's going in between these points here, okay? So a lot of this implicit differentiation is used for things that are not just one line, okay? Like a curve or a parabola. Think things that are like not one-to-one, right? Or not functions, right? A circle is not a function because it does not pass what? The vertical line test, right? So I want to find the derivative of this equation right here with respect to x. Can you guys do that? So I'm taking the derivative here. Oops. So I have to get that dy dx by itself. I'm going to first move over that 2x. And then how do I get rid of that 8y? Divide. This we could simplify to give us just negative x over 4y. And that is your answer for your derivative of that equation above. Okay? So using this derivative allows us to find the slope of the tangent line to this curve that we're going to look at just below here. Okay? Oops. It says, find the slope of the tangent line at this point, the square root of 2, comma, negative 1 square root of 2. Okay? So I have an x, I have a y. Can I plug it in? You betcha. So taking our x of the square root of 2, plugging it in for x. And then my y value of negative 1 over square root of 2, I'm plugging that in down there for y. We just got to be careful when we're simplifying. So negative square root of 2 divided by 4 times negative 1 over the square root of 2. It's the same thing as negative square root of 2 over negative 4 over the square root of 2. If I got a fraction and a fraction, I can multiply by the reciprocal. So I've got the negative square root of 2 times square root of 2 over negative 4. Which this is going to equal negative 2 over negative 4, which gives me 1/2. Okay, so my slope is 1/2 at that point, square root of 2, comma, negative 1 over square root of 2. Now we want to find the equation of the tangent line. Well, I have my slope. Oops, I have my slope. This is equal to m. I have my point. Can I write my equation? You betcha. I've got y minus negative 1 over square root of 2 is equal to 1/2 times x minus the square root of 2. So that right there is my function of the line that is tangent at that point, okay? So take a minute real quick. You can take a little break. I'm going to plug this in on the graphing calculator on Desmos, and I'm going to show you guys what this looks like with your tangent line and your actual function on here, okay? So you guys can take a break for a minute while I pull this up. Okay, so I went and graphed both of these equations in Desmos. Okay, again, this was our original function in red there of x squared plus 4, y squared equals 4. And then that point of 1.41 and negative 0.7, that's actually your point of square root of 2 and then negative 1 over square root of 2. So at that point, that is your tangent line at that point in time on that ellipse. Okay, does that make sense? So that is what you are finding. We're not just doing a bunch of math. That's actually what's happening. Okay, all right, this part E says to write the above equation explicitly. So that means like the above equation of the x squared plus 4y squared equals 4. If I was to write that in terms of just y, explicitly means it's solved for y. Could I do that? Yeah, right? Let's solve this for y. So if I solve this for y, I get negative x squared plus 4. I divide by 4. I get y squared equals negative x squared plus 4 over 4. And now in this case, if I'm solving this and I take the square root of both sides, at this point, we would have two answers, right? I have y equals positive and negative square root of the stuff on the inside. Okay, if I take and I plug in, well, two things. I could take the derivative of this function using the chain rule, right? I could set this whole thing, this is the same thing as negative x squared plus 4 divided by 4 to the 1/2 power, right? We agree? And then I would actually probably rewrite this as, in the parentheses, negative 1/4 x squared plus 1 to the 1/2 power. And then we could take the derivative of this, right? You agree? Let's do it. So this is going to equal 1/2 times this negative 1/4 x squared plus 1 to the negative 1/2 power, right? And then I have to take the derivative of the inside, which if I take the derivative of the inside, I'm really just taking the derivative of negative 1/4 x squared, which would be negative 2/4 x, right? Or negative 1/2 x. Do we agree? Okay. And let's just rewrite this so it looks a little bit nicer so that I can show you what happens. This negative 1/2 stuff, that's going to go down below, right? So that's all going to be down here. And that's all underneath the square root. That was this piece right there. And then with that negative, the 1/2 and the negative 1/2, can I combine those to give me negative 1/4 x, right? So that means I would have an x on top. Well, I could have the negative x on top and then a 4 down below from this, right? Okay. So we could solve this equation for y and then actually take the derivative of this function. However, doing all of this is a lot of work comparatively to what we did up here when I found my derivative of this negative x over 4y. That's the same thing as what we have here. This is the same thing as negative x over 4y. You guys see the negative x and the 4 pretty easily, right? the y part, well, y is equal to this thing right here, right? Which is also equal to what I have there in red, just written slightly different, yeah? So taking and doing the derivative with respect to x with implicit differentiation allows us to kind of simplify the process, right? This is a little messy, but it gives us the same answer, okay? All right. Let's look at the next page here. Okay, we are only going to go through example 7. We are not doing logarithmic differentiation, so stay with me for 2 more examples. Okay, first example here says find the slope of the graph. The graph is over here on the right. This is what it looks like, a little infinity symbol, okay? And this is the whole thing. We've got 3x squared plus y squared squared, and then 100xy on the right-hand side. Now, trying to solve that for y would not be a very fun time, okay? One thing I do want to point out is that on the left-hand side, I just have one piece that's being squared, right? Like, I don't have 2 functions that I'm multiplying together, right? It's just a number. This would be the same thing as if it was like 3x squared, right? So I don't have to do the product rule on the left-hand side, but on the right-hand side, I have 100x and times by y. So on the right-hand side, we're going to have to use the product rule. On the left-hand side, you're just going to have to use the chain rule, okay? So let's kind of go through this one together so that we're on the same track here. I'm going to start by moving that derivative, or moving that power down in front. So this becomes 3 times 2, which is 6. And then I'm going to rewrite everything on the inside of that parentheses. This is technically to the first power. And then I need to take the derivative of the inside, right? That's what our chain rule says. So I'm going to take the derivative of x squared. This is in relation to x. So the derivative of x squared is what? 2x. Okay. The derivative of y squared in relation to x is 2y times what? dy dx. And that is my left-hand side. Are we okay with the derivative of the left there? Okay, then I need to take the derivative of the right-hand side. So that means I'm going to take the derivative of this first piece here, 100x. The derivative of that is 100. And then I'm going to leave the function of y, not take the derivative yet. And then I'm going to add, and I'm going to take the derivative of the second piece here. What's the derivative of y? Well, with respect to x, it would be dy dx. And then I'm going to times it by my original first function here, which is the 100x. Okay, so you have to have that dy dx when you're taking the derivative of y. You're not alone. It's okay. Okay, looks a little gross, but are we okay there? Okay, then it asks us to find the slope. So instead of trying to simplify this for dy dx and solve for dy dx right now, how about we just plug in those values? Okay, we know that x is going to be 3, and we know y is going to be 1. So that's going to simplify a lot of that for us. Okay, so let's plug those values in. So I've got 6 times 3 squared, which is 9, plus 1 squared, which is 1. Then I've got 2 times 3 plus 2 times 1. And then on the right side, I've got 100 times 1. And I don't know what my dy dx is, so that's going to stay there. But then I've got times 100 times 3. Oops. Okay. So let's simplify this stuff. On the left there, what is 6 times 9 plus 1 going to give me? 60. So I've got 60 times, this would give me 6 plus 2 dy dx. And then that's 100 plus 300 dy dx. We okay so far? Okay, now here's where some of us struggle is I want to get that dy dx by itself on one side, right? But I've got parentheses on the left side. So what do I actually need to do first? I can't subtract 60 because the 60 is being multiplied.
Multiply that, or like distribute.
Distribute. So let's distribute that 60 to each of these terms here. So I'm going to have 360 plus 12 dy dx. Oh, 120 is what I meant to say. And then that equals 400 dy dx? No, I can't add those together, right? So 100 plus 300 dy dx. Okay, now I just got to get all my dy dx's on one side. So I'm going to move that 120 dy dx over to the other side. So 300 minus 120 is going to give me 180 dy dx. And then move that 100 to the other side.
It's just 100.
Huh?
It's just 100. Wait, oh.
So I moved the 120 over to the right. And then I move in the 100 over to give me 260.
Take that first, I guess.
Yeah. And then to get dy dx by itself, we have to do what? Divide. So dy dx equals that 260 over 180, which can simplify to give me 13 over 9. And that right there is your answer. What did I just find? The derivative, right, at that point of 3, 1. So if I look at the point 3, 1 over here, 3, 1, obviously it's not perfect, but this slope 13 divided by 9 is about 1.4 over 9. It's almost 1.5, not quite 1.5. But does that slope, if I were to draw a tangent line there, look about to have a slope of 1.5? Would you agree? Kind of looks like it crosses down here as well as right there, which goes down 1 and a bit. So yeah, I would agree with that. Good math. Nice job. All right, last problem here. Find the second derivative, which means we have to find the first derivative before we find the second derivative. Okay, so I'm going to give you a minute right now. Find the second derivative with respect to x given this function of y squared plus xy equals 25. And solve for dy dx. Okay? So solve for dy dx. I'm going to give you a minute. Try it out with your neighbor. And then I will go over it. Okay, are we all okay with that first derivative that I took there? Yes? Yes. So then if I solve this for dy dx, I'm pulling out that dy dx. And I end up with, after I do a little bit of math, dy dx is going to equal negative y divided by 2y plus x. Okay? We good with that? So like we subtracted y first, right? And then I factor out this dy dx from both of those to give me that 2y plus x. So I technically factored out, I didn't show a step here. I factored out 2y plus x, and that equals negative y, and then I can divide and have dy dx by itself. Yeah? Okay. So now from here I need to find the second derivative, which gets a little bit messier because we have a fraction, which means we're going to have to do what? The quotient rule, okay? So I'm going to move this out of the way so I have more space here. Let's take the derivative of this function here. So low d high, that means I'm not taking the derivative of the denominator, 2y plus x, low times the derivative of the top. The derivative of negative y is just negative dy over dx. Okay? Are we okay with that low d high piece there? And we're going to subtract high d low. So I've got negative y times the derivative of the denominator. What is the derivative of 2y? 2 times dy dx. And what's the derivative of x? Just 1. Okay, so that's low d high minus high d low. And then all of this is being divided by what? Low squared. So 2y plus 7 squared. Or plus x. Okay. So this is equal to our second derivative here. Okay. We could simplify this a little bit further if we wanted to, because I could actually solve this for y, could I not? Actually, wait. Never mind, I can't solve it for y. That's not what I meant to say. But I do know that my second derivative is equal to this thing over here in blue, right? So I could, again, this is another one of those like algebra is a little messy kind of thing. Could be a multiple choice kind of question, could be a free response kind of question on your AP test. They could plug this piece in for where you see dy dx and simplify it and give you the answer. So let's try doing that, okay? We gotta be real careful though when we do it so we don't miss anything. So I've got 2y plus x times this negative y over 2y plus x. I'm plugging in that dy dx piece. Okay, then it says minus negative y, can't do anything with that, and then times 2 negative y over 2y plus x. Plus 1. It's really kind of nasty. Yeah. This one should be positive, yes. Because it's a negative negative. Good catch. And then all of this is being divided by 2y plus x squared.
What? I don't understand.
So all I'm doing right here, Jacob, is I'm plugging in the dy dx pieces, right, where I have the blue there. I'm plugging those in here, and then we're going to simplify it.
I don't think I like math anymore. I don't like derivatives.
Okay, this one's just a little gross. It's okay. Now we need to distribute. Okay, so this y, I'm distributing to both of these things, right? So this is now going to be 2y squared plus xy, all divided by 2y plus x.
Can you cancel these
Okay.
two y's?
And then over here, I've got, this is a little messy. I'm going to rewrite this as negative 2y over 2y plus x. Because then I'm also going to multiply it by a negative y. So I've got minus a, let's see here, positive 2y squared divided by 2y plus x. And then don't I also need to multiply this negative y with this positive 1? Yes? To give me a minus y. And that whole thing is all being divided by your 2y plus x squared. Okay, so yes, we need to make this a common denominator here. So I'm going to multiply this by 2y plus x over 2y plus x. So this would give me over here negative 2y squared minus xy. And now things can start to simplify, right? So instead of this one, I now have this over 2y plus x. So what can I get rid of?
I'm so lost.
This 2y here, this negative 2y, I can get rid of this xy and this negative xy, right? All of these things cancel out. And I am left with just negative 2y squared divided by 2y plus x. And that's all being divided by 2y plus x squared. Which is really just the same thing. If I divide by my fraction here, right, I can multiply by the reciprocal. So this is the same thing as negative 2y squared divided by 2y plus x to the third power. Because this is to the first power down here, right? And then if I write 2y squared divided by 2y plus x times 1 over 2y plus x squared, that gives me 3 of those on the bottom, right? Yeah? Question? Where'd the xy go? Because I had an xy here and subtracting with that xy there. Yeah. Okay, so that was kind of a chaotic mess, yes? Again, this is why when I have you guys take the derivatives on tests and quizzes, you stop here at this point. Whoa, at this point right here for the second derivative, okay? If you will sometimes have to solve it, okay, because it'll show up on AP tests and maybe multiple choice questions in future here, simplifying it to give you that answer, okay? A little gross. That's your final answer, though, if you are finding the second derivative of this function. So homework is posted on Schoology. There are 9 questions, so try them out. There's not a lot of space on there, so you'll want to do it on a separate sheet of paper. But yes, try them out. We'll go over them next time. We'll spend another day on implicit differentiation, so that way we feel comfortable with it.